transportation problems, we have some sort of grid or chart associated with it, just because there is a lot of information that is jam-packed inside of something if you write it out in paragraph form, okay? Now, in order to talk about all of this, we need a little bit more information, and we actually have enough here that we can talk about it. So if we have X with a subscript IJ, this would be the number in millions of kilowatt hours of electricity that's actually shipped between plant whatever, I, and sent to city J. So in this case, the plants are actually producing or harnessing the electricity. Now, in terms of if we want to find the minimum cost to get all of the power from the plants to the city, it turns out it's this function right here before the ST representing such that, okay? So in terms of here, what do we have? If we're looking for that total cost of shipping the electricity, this would be the cost of 8 per units from plant 1 to city 1 times the amount of electricity shipped from plant 1 to city 1. And then notice the cost associated from plant 1 to city 2 gets multiplied by the amount shipped from plant 1 to city 2, and so forth. You can build this entire thing where you pull out the grid, this 3x4 grid here of all the costs, and multiply it by the associated amounts that you ship between. Now notice the additional inequalities that we have down here. Additionally, we add x11, x12, x13, x14. In other words, all of the x's associated with this row right here. And what did all of these x's represent? It represents the total amount of electricity that plant 1 shipped out to any of the 4 cities, or really all of the 4 cities. Well, why would I have this less than or equal to inequality right here? However much they ship out to the different cities, plant 1 only has a supply of 35, so you can't exceed that amount of 35. So that gives you an upper bound in this sum. You can do the same thing for each of the plants. So for plant 2, if you add up across the row, so all of the amounts that it ships out to the 4 cities, you can't exceed 50. So that's this inequality. If you add up all the amounts that are shipped out from plant 3 to cities 1 through 4, the total amount shipped out can't exceed their supply of 40. So that will give you this inequality. Technically speaking, the next ones can also be inequalities, but in reality, you try to make them equals. Why? Because these guys are going to be adding down the columns. So if you add down the columns, this is the amount of electricity that city 1 received. So city 1 would receive x11 amount of electricity from plant 1. City 1 would receive amount x21 from plant 2. And city 1 would receive amount x31 from plant 3. And if you add all those amounts together, it will hopefully meet its demand. Now, why would I say technically speaking there's actually normally a little inequality here? While you want the demand to be totally met, what do we know? We know if we're in short supply or don't have enough stuff to go around, the amount that the plants actually ship out might be too little for what the demand actually is, and that's where you can get this guy to technically be an inequality. We're not going to look at those cases because they have a little bit of a different way that you have to deal with them. It's in the initialization, you have to deal with them a slightly different way, and it's more complicated than what we're going to be doing. Okay. And so then you do the same thing for each of the 4 cities, add down the amount shipped out here in what would correspond to column 2, and it's supposed to equal its grand total of 20 because city 2 wanted 20 units of electricity. Add down the guys associated with column 3, it's supposed to equal 30 because city 3 wanted 30 units of electricity. City 4 also wanted 30 units of electricity, so adding down those columns would be giving you the last equation. And here, note the assumption is for any of your I's and J's associated to your electrical plants and cities, the X, which is the amount of electricity shipped between the electrical plants and the cities, is greater than or equal to 0. Why? Because that's assuming that the direction is always going from the plant to the city. Okay, so this is the type of question that's behind the scenes, or really what you're given at the beginning of a transportation problem. You have some sort of situation of 2 groups of entities, and you're trying to move something between those 2 groups of entities, and there's a cost associated. And what you're trying to find is you're trying to minimize that cost. Okay, Now, in terms of what we're going to see, we're going to throw this all into, well, what do? We deal with graphs. So let's see how this would actually correspond to graphs. So let me throw up the other thing. Let me unshare what we were just dealing with, and now we should be able to see this at full size. All right, so general description. Let's actually make that a little bit. All right, so general description is, in terms of the graph that's behind the scenes, is you actually have a complete bipartite graph. It is a directed bipartite graph. And what we're going to have is you have a certain number of supply points, and that'll be one side of your vertices from which your goods or whatever they actually are shipped. And your supply point I is going to have some supply that's the most that they can ship out. So that'll be given for us in whatever units you have. This will also give us with what are known as the supply constraints. Those are those inequalities we just looked at that said, hey, in total, all the amount that's shipped from supply point I can't exceed a certain number. Specifically, it can't exceed S1 here. We're also going to have a set of demand points where the goods are shipped to. Demand point J must receive at least the units. And in terms of how your author puts it together, which is the slightly simpler version, is we're actually going to create demand constraints here, and we're going to assume that we actually meet the demand in this case. In other words, that we actually get equations instead of inequalities. Okay. In terms of notation, there are two notations to worry about. One is X with subscript IJ. This is the same as what we talked about in the PDF example we just looked at. This is the amount of goods that are shipped from supply point I to demand point J. Okay. The second notation that we're going to use is the same notation we use when we're in the traveling salesman problem. So we have a cost to C, subscript IJ, and this is the cost that is involved to ship some item from supply point I to supply point J. Okay. Now, that handout was actually a different example from what we're doing, so I'm going to get rid of that. When I originally made these notes, I thought I had misremembered which one was on the PDF. Okay. So here's an example, and this is the example we're actually going to work through for the rest of today, and depending on time into tomorrow. So instead of giving you all the information of how to solve one of these transportation questions at the very beginning, instead what I'm going to do is actually give you the directions, the strategies, and the formulas as we go about solving this particular transportation problem. Now this particular transportation problem is small enough, you could probably just brute force it just off of this directed directed bipartite graph, and just wiggle around where you want to ship what and get to the answer. It is, however, also large enough that that would take a fair amount of time unless you're super lucky. But some of us are super lucky. Not me. Normally I would pick automatically something that just is not the right one. At least when I was first starting. All right, so in this case, our assumption is we have 3 warehouses. So this is where our goods start. We've got 2 stores in play here. Each warehouse has a certain supply. So warehouse number 1 has a supply of 40 units. Pick your favorite units. Pick your favorite good that's being shipped here. Okay. Warehouse 2 has a supply of 60 units. Warehouse 3 has a supply of 30 units. Don't assume necessarily a unit is one item. It could totally be like what we have in the last example with the electricity. It could be that your units are actually in the millions or the thousands, or maybe it is actually just one unit and it's a really, really tiny warehouse, or a really big item. Maybe they're selling tanks. I don't know. Or houses. Although how you would put houses in a warehouse. Anyway, moving on. So you've got your warehouse, and then each of these 2 stores demand the following units. Store 1 wants 60 units of whatever your items are, and store 2 wants 50 units of whatever your item is. Notice here the directed edges of this graph are specifically indicating the supply lines. So we're going here from the warehouses to the stores. The assumption here is we're not sending stuff back from the stores and returning it to the warehouses. The assumption here is that we are only going from the warehouses to the stores. Okay, so in that direction. Now, we're also going to have a cost associated with each of the different things, and then we're going to be dealing with that one. It actually is quite similar to our augmenting flow algorithm. We are, however, going to go about doing it differently, okay? And one of the things that we're going to be doing differently is we're not going to create a single source or a single sink, and we're also going to, the extra thing that we have here is we've got the cost associated. So we don't have a limitation in capacity, as in it doesn't limit you of how much stuff you can ship along the edge. All that's limiting is the cost per unit. So that's where it actually differs from your augmenting flow algorithm. Augmenting flow algorithm limits how many items you can ship along one edge right here. Where this one is, it's more of a minimalization problem where you could ship all 40 units across this edge if you wanted to, but is that the best thing based on cost? So it's a different way of limiting what you push across your edges or ship across your edges. But you're right. At this point in time, it looks almost identically the same. So let's put the costs involved. So the cost to ship from warehouse 1 to store 1 is going to be $4, or pick your favorite dollars. Maybe it's $4,000 a unit. I didn't write down the unit, so I'm just going to write down the 4. The cost to ship from warehouse 1 to store 2, the price there is 2. So 2 of whatever your units are. Maybe it's a single dollar, which is typically how these guys are written, or maybe it's actually $2,000 and we just left off the 0. I'll just go with a single dollar. Okay. So then the cost to ship from warehouse 2 to store 1 is $6 per unit. The cost to ship from warehouse 2 to store 2 is $7 per unit. The cost to ship from warehouse 3 to store 1 is $5 per unit. And the cost to ship from warehouse 3 to store 2 is $6 per unit. Now, this is an extraordinarily simple example. You've only got a grand total of 5 vertices, and notice already there's a fair amount of information going on. If you were in some sort of situation where you actually had to create a transportation problem to solve whatever situation that you were in, whether it's in a future math class or outside of an academic situation, it is highly unlikely that you actually have this few vertices in your graph. Typically, you'd probably have a few more stores, you'd have a few more warehouses, and as soon as you start adding in the extra warehouses and stores, the complexity goes up quite a bit. So we're going to stick, though, with a small example. Okay. But the process is exactly the same regardless of how many warehouses or stores you have. Now, in terms of the total cost, in other words, our cost function, the cost in total to ship all the goods going from the 3 warehouses to the 2 stores is simply going to be the sum of what amount of goods you shipped along each one of these directed edges multiplied by the unit cost associated with each one of those edges. Okay. So once we actually put in where the goods are shipping, you just multiply the amount that you shipped along each edge by the cost associated with each edge and add up the total. That's the total cost of that particular way of shipping goods. Now, the goal of the transportation problem, so let me actually write the goal here. Is we would like to minimize our cost function. Minimize the cost function. Now, why? Because if this was maybe some company, and maybe the company owned these different warehouses, in that particular case, they would like to minimize their cost in shipping out to whoever they sell to. So that would be a reason of minimizing your cost. Plus, almost any time you talk about a cost function, you want to make your cost as little as possible. Just because. Just a second. Let's see. It depends. So the question that was asked is these unit costs, how they're calculated. In terms of these problems, this is the stuff that you would be given at the beginning of the problem. You would be given how many warehouses, and we'll call everybody on this left side warehouses because this is going to be our supply side. And you'll also be given how many stores. So I'll call these guys stores regardless of what you actually have. And this is on our demand side. You'll also be given what the supplies actually are to each supply point, what the demands actually are with each demand point. And while I wrote them in black here, you have to be given those costs ahead of time. But in terms of actually figuring out the cost, if you were, say, the person hired for this company to put together this model and then figure out the answer, yeah, these costs here, if it's truly where there's a truck driving between warehouse 1 and store 1, it would be things associated to it like your gas, like maintenance on the vehicle, if there's toll roads they have to go over, if all of that stuff that's attached to traveling on this particular route. But yeah, so things like in terms of these guys, the supply is typically not related to your cost. It's typically not related to your demand, although realistically it probably is to some extent. But in terms of what you're given, these guys are 3 independent things. This is specifically what warehouse 1 is doing. Supply or S2 is specifically what's going on in warehouse 2. And then the costs are associated with, like, specifically warehouse 2 connecting to store 1. In my head, I always picture it, all right, if warehouse 2 is located in this city and store 1 is located in this city, well, it's X miles away, and you calculate, like, gas, lodging for the driver, or food, budget, those sorts of things. Okay? But at least from what we're going to see, all of the stuff that you see right now, including the cost, are going to be given to you. Okay? So you don't start your transportation problem until you have all that information. All right, so our goal at the end of the day is we want to minimize this cost function, and we're actually going to do that inside of the graph, although I lie. These problems get so complicated so fast, it turns out the strategy that we're going to use is we're going to actually use something called a tableau. A tableau is taking all of this information that we have in our bipartite graph with the extra information of the supplies and the demands and the costs and putting it in a chart. Okay. Now, the final answer here is going to be a spanning tree. Well, I guess it doesn't have to be a tree. It's going to be a where we select, specifically we're going to select how much goods to transport across each edge. It's totally okay if we decide not to transport goods across edges. So, for example, we see edge here going from warehouse 2 to store 2 has a cost of 7. Maybe you decide, hey, no, it's not going to happen. Maybe up here with warehouse 1, looks like because the costs are so low, this would be something that, hey, maybe we're going to ship out all of the goods stored at warehouse 1, and all of those goods would be completely depleted and shipped out. Maybe it would be shipped only to store 2. Well, there's still some left over, so you got to get some of the extra stuff from somewhere. Maybe you ship it only to store 1. Still, you left more that store 1 wants, so somebody else has to supply store 1 too. Or maybe it's split between the 2. Okay? And that's what we're going to have to figure out. And this here is the same thing that we did in that PDF that we saw at the beginning, except now it's in the, for each warehouse, you add up all of the guys shipping out from the warehouse, and it has to be less than or equal to your total supply. And in terms of the demand, if you add up all the amounts coming into your store, it's supposed to equal your demand. Okay. Yes, so this is very much what looks like a network flow problem, but we put the extra bit. You can't see me do it, but I just moved my hands like slapping something on top of a network flow problem. We then slap the additional cost on top of like a network flow problem. And that's why we can't use the exact same algorithm we had before. All right, so here's our goal. Our solution is going to be where we get all of the values for the X's, the actual amount that we transport between all the different warehouses and all of the different stores. Now, what do we want? We want to meet the demands. So that means when we add it up, all the stores got what they ordered, and we don't exceed any of the possible supplies, so no warehouse can ship more than they actually have. Okay? And here's the key thing, you minimize the total costs involved. So in terms of what we're going to do, when you get an initial solution, just like in a network flow problem when we had an initial flow, all we were looking at was putting a flow on the system so that it actually was a flow, and then we adjusted it. In terms of here, if you wanted an initial solution, you would put in a way to ship goods between the warehouses and stores, and you don't necessarily focus on the cheapest way to ship the goods from the warehouses to the store. And then when we run through our transportation problem, we'll actually adjust that and fix it and get it to the actual cheapest way of transporting the goods from the warehouses to the store. Now that being said, there's actually some standards of how you do that initial solution, and I'm going to show, and we'll go through those. Okay? So first thing though is looking at the Transportation Tableau, and this is the way that people work through transportation problems. So the Transportation Tableau, the buzzword tableau right here, is totally just talking about a chart. Okay? So people often, I wouldn't recommend it, but people often put it in an Excel spreadsheet. Some stuff is lost if you do it only that way, so let me show you the way that makes it so nothing gets lost. Okay? So instead of using our bipartite graph, we're going to use a tableau. The cell in each one of the tableaus, in other words, think of like a spreadsheet, the cell in the spreadsheet is corresponding to the appropriate X value, the amount that we're shipping between warehouse I and store J. So specifically the rows, so row I, column J. Row I is going to correspond to your warehouse. Column J is going to correspond to your store. Okay? The label in the cell, and I'll show you what the label is in just a second, corresponds to the cost associated of shipping goods along that route. So from warehouse I to store J. So with the example that we just had, the one that's right up here, we had 3 warehouses and we had 2 stores, so we had a grand total of 6 edges involved, and there was a cost associated with all of those 6 edges. Okay? So when we put this down here in our tableau, first thing that we do is we write down all of our warehouses. Our warehouses are always over here on the very first column, so associated with each row, and then we list out all of our stores. Okay? So notice this cell right here corresponds to the edge that goes from warehouse 1 to store 1. This second cell right here corresponds to the edge going from warehouse 1 to store 2. Now, I'm going to put in some extra information. First thing deals with our supply. Warehouse 1 has a total supply of 40, or had a total supply of 40, so I'm just going to copy that down from above. Warehouse 2 had a total supply of 60. Warehouse 3 had a total supply of 30. Okay? Now, if we look at the stores, store 1 had a total demand of 60, and store 2 had a total demand of 50. These guys over to the side, let me grab a different color. The supplies, specifically the row that corresponds to warehouse 1 all the way until we got to a supply of 40, these guys correspond to the supply constraints. So what does this mean for us? This means that once we figure out how many units of goods are shipped between warehouse 1 and either of the 2 stores, the total amount shipped to store 1 and to store 2 from warehouse 1 cannot exceed 40, so this sum of those 2 cells can't exceed 40. Yeah, this is, operation research is almost 100% a combination of graph theory, what we're into here, and economics together. So yeah, what we're covering right now is totally a thing that would be covered in an operations research class as well. This is where those 2 courses overlap. Okay. Actually, one of the ways you can think about operations research is that it is an applied graph theory course, which graph theory is not a prereq for operations research in our university. So that's always fun, because it's pretty rare for people in those courses to grad graph theory first. If you read down the columns, this talks about your demand constraints. So once we track how much we want shipped to store 1, we want all the cells in column 1 to actually add up to 60 here at the bottom. Okay? So that would be the idea here. Okay? What some people do is they actually, in the tableau, this last row of demand and this last column of supply are often sort of just like scratched work on the outside of the chart and not actually looking like it's inside of the table like what I've got right here. Okay. Now, last thing that we need to worry about in terms of our Tableau, and this is just setting up the given information, it's not doing anything with it, is putting in the labels. Now, the labels are the costs associated with each cell. Okay? So the cells are associated with the total amount you're going to ship between a warehouse and corresponding store. And now we put in the cost, and there's two ways to write the label. But all of the ways that you put in the label is you have some sort of way of sort of cutting off a corner. Some people actually write it like this, where they put a little box to the side. Not going to lie, the first time or first number of years that I did transportation problems, I always did it like this because I thought that looked nicer. But if you're doing this fast and you have to write a bunch of tableaus, it's definitely quicker to do the one that looks like you have that corner triangle right there. Okay. And we'll put in the cost associated to these other ones. I'm going to do the corner triangle just because it's quicker to draw. So here in Warehouse 2 had a cost associated of 6 and 7 to ship to store 1 and 2 respectively. And Warehouse 3 had a cost to ship to stores 1 and 2 of $5 and $6 per unit respectively. So this here would be your initial Tableau. So let me actually label that. So this would be the initial Tableau. And this is only of the given information. There is no work involved whatsoever. There's no guess of how to ship anything. This is just the initial Tableau. Now, before we go on to start making an initial guess of where we should start shipping goods from warehouses 1 through 3 to stores 1 and 2, we do have to talk about something known as balancing your transportation problem. Okay? So balancing the transportation problem is something that you have to occur if the total supply and the total demand are not equal to each other. If the total demand is bigger than the total supply, the fix is a little bit snarly, and that's the situation we're not going to deal with in this class, in part because we literally have like 30 minutes left today and then the beginning of Monday left to talk about this. So if the total demand is less than the total supply, that is a fix that we're going to look at. And the fix is you put in a fake store, okay? It's technically called a dummy demand point, but it's basically you put in a fake store, and this fake store has a demand that's equal to the excess supply. In other words, the amount of extra supply that was not demanded by the stores in your system. Okay? What we're going to do is we're going to assign a cost of $0 along any of the edges associated with the fake store. Along any of the additional cells in the Tableau will have a cost of 0, and that is because this fake store isn't real. It's only a way to make our algorithm actually work in the future. Okay. So what we're going to do is we're going to take this exact same Tableau we just had, but we're now going to insert an extra column, essentially a store 3. Okay. So here's what we had previously. We've got all of the cost on the stores 1 and 2. That won't change because it's a little bit more complicated than that, which is why we're not going to talk about it. If you guys are interested, I think I have notes somewhere that I can go scrounge up to go find it, but that was a while ago because those would have, the last time I dealt with that fix was actually when I was teaching an operation research course. So I have to go find those notes somewhere. In terms of dealing with the fake store, though, the fake store is easy to deal with. So here's what you do. You look at your total supply, you look at the total demand. So let's do a quick check here. If we're looking at our total supply, how much total supply do we have? Anybody happen to add that up while I was trying to get a different pen color? Yep. So total supply is 130. Did anybody happen to get what the total demand was? Should be 110? Yep. So what's the difference between total supply and total demand? Yep. So that means the amount that you put here in the fake store is that difference of 20. Okay. Now, extra thing, since it's a fake store, since it's not really there, it's just a way to make our algorithm work in the future. The cost associated of shipping from warehouse 1 to fake store is nothing because it literally just stays in the warehouse. The cost of 0. The cost for warehouse 2 to ship to this fake store is again 0 because what it really means is you just left the warehouse sitting this goods sitting in your warehouse. Same deal with the last cell, or the last label for the last cell. And at this point, this is the fully initialized Tableau. So fully initialized Tableau. So now, what do we do with this thing? In other words, how do we find an initial solution? It turns out that there are three main methods to use to find an initial solution in the transportation problem. I will tell you about all of them, but we're only going to do one of them. We're going to do the easiest one. Okay? So the three ways of finding an initial solution are the northwest corner method. That's the one that we're going to use. The minimum cost method and Vogel's method. Now, there are claims to fame and advantages to all of them. Northwest corner method is the easiest one. No lies, that's why we're going to do it. Okay. The minimum cost method one is one that is less easy. It takes a little bit more thought process to actually do it, but the initial solution that the minimum cost method yields is actually closer to your real solution that has totally minimized the cost. Okay. So this one here is closer to the optimal solution. Optimal solution. And Vogel's method, named after a guy whose last name was Vogel, this one actually for simple transportation problems typically gives you the actual solution with, definitely takes more work. This one is the hardest of all. So most complicated, but gives you the closest solution to the actual solution. Now, I'm not going to go over, well, I should say closest solution, gives you the closest solution to the optimal solution. Now, I'm not actually going to go over all three of these guys. I just wanted to give you their names. So if you wanted to look them up, you totally can. For us, we're actually going to look at the northwest corner method. It is the fastest one to get an initial solution for your transportation problem. It's the easiest one to calculate. It is, however, the one that your initial solution is the furthest off from the optimal solution, unfortunately, which just means what? It means you might have to go through your algorithm for the transportation problem one or two extra times as opposed to these guys down here. So let us look to see what the northwest corner method is. The northwest corner method goes as follows. It says you look in your Tableau. Okay? You have to have already set up your Tableau with the fake store if you needed a fake store, with the supplies on the side, with the demands on the bottom. You have to have all of your costs already in the labels. So what you do is you identify your northwest cell remaining in the Tableau whose supply and demand is positive. Okay? Now, northwest here means what? It means you're looking as high up in your Tableau as possible, north meaning up, and west meaning you're looking the most towards the left. So it is totally a descriptor in terms of the name. Actually, both the northwest corner and minimum cost method are descriptor names. Northwest corner, look up and to the left. In other words, look north and look left. Okay? Then, what do? You set the amount in that cell that you've identified as the northwest cell that's currently in play. You set the value, the amount that's going to be traveled along that edge in the bipartite graph to be the minimum of however much supply and demand is left in your row and column. Okay? And we'll see how to do that in just a second. Now, once you've assigned a value in that cell, you subtract the amount of goods that you've used up in step one from that cell's row and column. From the total supply in that row and column. Now, what will happen is when you do this subtraction, since you tried to grab the minimum of the current supply and demand across your row and your column, you actually identified one of those two guys, and either the total supply or the total demand is going to zero out on you. Okay? Could be both if they were equal, but one of these two guys is going to end up with zero. Okay? In other words, you've depleted either the supply or the demand of that row and column, and you repeat these steps 1 and 2 until all of your supply and demand is depleted from all of the rows and columns. So let's see how this works out in an example. Okay? So I just copied down where we were currently at with our Tableau, and let me actually go ahead and do a slightly different color here. Go with blue. Okay. So here, in the very initial Tableau, we have no values whatsoever in any of the cells. You look north and west. Northwest is going to be here, warehouse 1 to store 1 cell. Okay. You then look at this demand for the store was 60. The supply for the warehouse was 40. You take the smaller of the two values because you can't in any cell exceed these values. So we'll write down a 40. Now, how did we get that 40? So this is the first step. X11 equals 40, and that was because we looked at the minimum of the supply of 40 and the demand of 60 in the associated row and column. Now, at this point, you adjust the supply and you adjust the demand. In row 1, we've used up all of the supply, so this supply is now 0. Okay? This supply has been depleted from warehouse 1, so warehouse 1 is not going to ship to anybody else. These guys here will not get numbers in them, and if you don't have numbers in them, by default, that means 0 for that X12 and X13 here. Okay? Now, when we adjust our demand, store 1 has actually received 40 units, so that means there are 20 units left that they're still demanding. What just happened? My thing just resized on us. Just a second. Ah! There we go. Okay. So we still have 20 units of goods that store 1 is demanding. So what happens, that means somewhere warehouse 2 or 3s need to pick up that additional. Now, next thing we look at, this first row is now out of commission, out of play. So in the remaining 6 cells, all 6 of them dealing with shipping from warehouse 2 and 3, we look for our next northwest corner. North as high as possible, so that's row 2. West as far left as possible, so that's store 1. So we look here and we try to figure out the maximum value we could put in. Supply for warehouse 2 is at 60. Demand for store 1 is only at 20. So we're only going to put 20 units in for that cell, which tells you X21 is going to be 20. And that was because we looked at the smaller of the two values of the supply of 60 and the adjusted demand of 20. Okay. Now, at this point, we adjust the supply and demand. So the supply of warehouse 2 goes down by 20. So there's 40 units of whatever this stuff is at warehouse 2. Now, store 1 has got the additional 20 units it requested. So store 1 is happy. It's not going to demand anything else. Notice what this means. This means row 1, column 1 have been depleted in terms of their supply and demand, so they are out of play. We are only looking at 4 remaining cells in play. Which of those remaining cells is the one in the northwest corner? What do you guys think? Yep, so it would be the cell warehouse 2, store 2, or 2. So here we look at the supply left in warehouse 2 is 40. Demand of store 2 is still all 50. So what value should we put in that cell in location 22? Yep, we should totally put in 40 units, and that 40 came from the minimum value of 40 versus 50. We then adjust the supply of warehouse 2. We shipped everything to store 2, so it's been depleted. And store 2 got 40 units it wanted, so it has 10 units left it's still trying to find. Now, notice what happened. Both the top row 1 and row 2 currently have been depleted in terms of their supply, so only warehouse 3 is still shipping stuff out. Store 1 has had its demand met, but store 2 and the fake store have not had their demands met yet. So if we use our northwest corner method, who's the cell that we should focus on next? Where should we go next? These are the only two options. Yep. So we should look here at 3, 2, warehouse 3, store 2. If you want to reference it, it actually would be X32. Otherwise, you're talking about a cost. But yep, it'd be this cell right here. And what number should we put in that cell? Yep, perfect. So we'll have 10 here. 10 was the minimum of the demand left for store 2 and the supply left in warehouse 3. So we adjust the supply left in warehouse 3. It's got now a supply left of 20, and store 2 has had its demand fully met. Now, at this point in time, once all of your stores have had all of their demands fully met, what should happen is you have had no numbers put in the fake store yet, and the last thing left is the very last cells that you enter in would be all the stuff dealing with your fake store. So let's check to see if that worked. Yep, we only have this one cell remaining in position 3-3. We have the fake store is supposed to get a grand total of 20 units. We have exactly 20 units left in warehouse 3. So this tells us warehouse 3 is the warehouse that is going to end up with those additional units left in his warehouse. And then if we actually wanted to close out the problem, we would say, hey, our supply and our demand got completely depleted in that last remaining row and column as well. This now is your initial solution. Now, one of the things that we do with the Tableau is it's a little bit fancy. So what this reads is all of these color-coded numbers, just to indicate which step we were on, are the actual values associated with X11, X21, X22, X32, and X33. So those would be the amounts that you're shipping from your warehouses to your stores. Okay? Any cell that is empty, you're assuming you're not shipping there. So by default, any empty cell has a value of 0 for the X's associated with those empty cells. Don't include the zeros. Okay? There is a huge difference in terms of cells with a value, even if that value is 0, and cells without a value. What's actually going on behind the scenes is we are building a spanning tree. These values right here we're building a tree. These values with numbers are in your tree. The values without the numbers that are by default zeros, these are your guys that are not in your tree. Okay? So that is actually going to play a huge part in your algorithm in the future. Now, if you actually wanted to figure out the cost associated with this initial solution, what you would do is you'd multiply the 40 times the 4. Anybody that doesn't have a number in it would zero out. You don't worry about it. The 20 would be multiplied by the cost of 6. The 40 multiplied by a cost of 7. So notice you multiply your label times your X, your value in the actual cell, get all of those products and add them up, and that would be your total cost. Okay? I'm not going to do it right now, but I can tell you that this one here is not actually a cheapest cost. We're going to have to adjust it. Oh, and I left extra space to do that work down there to the side. Well, now, in terms of what we just did, so this just summarizes what we just did. At each one of those steps, we should have had one of the row or columns be completely depleted of the supply or demand. The solution is going to correspond to a spanning tree on your bipartite graph. So these guys here are indicating the edges that you would use in terms of that spanning tree. And if at any step we use up all of the supply and all of the demand, we need to, you can't get rid of 2 rows and columns at the same time, basically. Because if you actually do get rid of both the row and the column at the same exact time, we'll actually, instead of getting a spanning tree, we will get a forest instead. In other words, a disconnected graph. 380 looks similar. I didn't actually add up the cost before, but that looks vaguely similar because it was in the 200s, I believe, when I was going through it earlier. Not this one, but the next iteration through. All right. Now, how do we actually adjust this initial solution to somebody that's got the cheapest cost? This is where the algorithm actually starts. So what we've done so far is we just set up our Tableau, and then we put on an initial solution. So the thing that we're going to do in order to calculate or get that solution better, in other words, cheaper overall, is we're going to calculate something called selling prices. I don't care if you remember this term or what. I don't even care if you remember what they correspond to. These are totally a way to manipulate your how much goods you're shipping along each edge, to manipulate it to get the cheapest thing possible, to adjust that value accordingly. So to some extent, it's kind of like throwing some extra information on there, like when we do our augmenting flow algorithm. Not the same thing. It's vastly different. But in terms of the idea, the thinking process behind it, that's sort of what's happening. There's sort of helper variables to fix up the edges we've chosen so far and the amounts we've put on each edge. So the symbols here are U's and V's. UI is considered the price of the item, the unit price of the item at warehouse I. VJ is considered the selling price of your good at store J. And if you actually add UI to the cost associated with traveling across the edge from warehouse I to store J, that should give you your selling price. Notice the store does some markup, okay? And that's as simple as we're not going to make it any more complicated than that. Now, in terms of what we're going to do is we're actually going to implement this algorithm differently than how your book talks about it. Your book does something a little stupid at this point. This one here is the one that's easiest to see. So what we do is we actually set U1 to some arbitrary value. Typically, people set it to either 1 or 10. And then we're going to solve for all of the other UIs and VJs with the following equation. We're going to say that the cost is equal to UJ, take the same subscript J, minus UI, same subscript I right there. Okay. Now, why can we go ahead and just set U1 to an arbitrary value? Turns out this is an issue back from linear algebra. I'm going to hand wave a little bit through this, but to give you a little bit of an idea of the linear algebra thing. So the idea here is, actually let me go ahead and just write it right up here. Different color, so it's a comment. Okay. So what we're doing basically is we are solving for all of the edges that are currently used, edges in your current solution. Okay. Note that means we don't actually have to solve for all of these little UIs and UJs in the entire system. And it turns out that the property that we're using to allow ourselves to do this is actually a linear algebra property. Here's our linear algebra property. It goes as follows. If you have n minus 1 constraints out of a total of n constraints satisfied, and satisfied just means met, satisfied, or are true, then it turns out all n of the constraints will be satisfied. So that's the property that we're using here, is this guy can be arbitrary because it would be like the nth constraint, if you will, to some extent. Now, your author at this point also throws in a lemma. He throws in a lemma 2 right here. And lemma 2 actually talks about calculating the total cost of your solution. I'm not going to lie, it's a nice way of breaking down your total cost of your solution. It says, hey, the total cost of any solution is cost times the amount of goods you ship along the associated edge and add them all up. You can also look at it if you're specifically looking at your across your stores or across your warehouses, where you can actually pull these selling prices and these the U here, which was the price of the item at the warehouse, and you can actually break it up that way. I'll be honest, I don't normally do it that way. You have to have this to make everything we're about to do work, but it's not something that in and of itself you necessarily use when you're working through the problem, that is. All right, so let's actually see how these U's and V's help us. Okay? So here, I've went ahead and copied down the exact same Tableau we had with the initial solution that we found with our northwest corner method. One of the reasons why I forced us to do northwest corner method, besides us having to know one of them, is because I totally prepped it up with that one right here. Okay. So what you do, the first thing you do is you look at all of your solution variables. Oops, did not want that color. So all of your solution variables are the cells here that actually have something in them. These guys are actually called basic variables. And that's something that should actually have been told in linear algebra, but most people don't actually tell you that term in linear algebra. So if you've never seen the word basic variable before, don't worry about it, okay? So these are specifically the cells that are in your solution. So what we're going to do here is when we look at all of the cells that are in our solution, we're going to look at our cost. So C11, I'm looking at this cell right here that has a 40 in it. The cost associated with that particular cell, and this is the formula that I'm going to use. It's that same formula we had a second ago, which is the cost is equal to V minus U, where the subscripts on the V and the U correspond to the subscripts on the cost function. Okay. So here at cost 11, this here is supposed to be V1 minus U1. So notice what happens. This is in actuality 4 equals V1 minus U1. And then I'm just going to walk down for all of these other formulas, and then we'll go back and solve for them. So then we'll look at cell 21. So cost 21 is supposed to equal V1 minus U2. The next cell we have is 22. So cost 22 is going to be V2 minus U2. The next cell we have is in row 3, so that's 32. So cost 32 is equal to V2 minus U3. And the last one that we have is in cell 3, so cost equals V3 minus U3. Now, we actually know what the cost is associated with each of these C values. Actually, we know the cost on all of the cells. So we'll go ahead and replace the C's with the actual values and then solve. So then when we rewrite all of these guys, we'll have then a 6 equals V1 minus U2. We'll have a 7 equals V2 minus U2. We'll have a 6 equals, and a 0 equals, the 6 equals V2 minus U3. And lastly, 0 equals V3 minus U3. So we will set U1 equal to 10. And from there, we should be able to solve for all of the other values. Please note, if you set U1 equal to a different value, like 1, which is the other common thing to do, what will happen is all the values for U and V will just be scaled to a different level. And that's actually okay. It doesn't get you to the right solution, because even if all your prices have been consistently depressed across the entire system, you're still going to be able to figure out the correct edges to use to get your minimal cost. If all of your costs have been multiplied by a factor of 10, maybe you started with 100 there, what happens, all the costs are inflated, but across the board, the same edge will still give you the same lowest cost solution. Okay. Now, here's why we actually set that a first value equal to something, because now using our first formula right here, 4 equals U1 minus V1, we know that U1 is 10, that means we can solve for V1. And since the solution is representing an underlying spanning tree, as soon as you know one of the values, you'll be able to solve for all of the other values. Maybe not in this order, but you'll actually be able to solve for all of the other values. Okay? So V1 here, if we subtracted 10 to get 4, has to be 14. Now, since we know V1, we can solve for U2. U2 should be 8. If we have 14 and subtract something to get 6, if you subtract 8 from 14, it should give you 6. Once we have U2, we can solve for V2. And if you still can't solve for both of these, you guys skip it, and you'll be able to solve for some equation further on down, and then you'll just have to backtrack. Okay? Now for V2, we're supposed to subtract 8 and get 7, so that means V2 should be 15. To get U3, we have V2 is 15, so something subtracted from 15 gives you 6, so that one should have been 9. And lastly, anybody got what V3 is going to equal? Yep, this one would be 9. That's one of the nice things if you have one of the solution variables are actually inside of your column associated to the fake store. It means your U and your V entities are going to be exactly the same, so that's a nice one. So these are our values here for U's and V's. Now, the question, of course, is what do these guys get used for? And it turns out these guys get used for figuring out which edge to kick out of the solution and then which edge to add to this solution. So we're going to look at that next. Okay? So if you determine which edge gets added to the solution, officially this is called the pivot. You're only going to add one edge at a time for each iteration of this algorithm. And when you add one edge, what happens is the underlying spanning tree actually has a circuit that closes, which means you have to kick out one edge, and you kick out one edge on that closed up circuit. Okay? So what you do is you consider all of the edges or the cells that are not currently used in the solution. That means in the Tableau, you're looking at all of these blank cells, and that's why it's really important to have blank versus filled in cells. Okay? You're then going to calculate an adjusted cost, and this adjusted cost, I put a little tilde over the standard symbol for the cost. It's the same formula of V minus U, but then you subtract an additional cost right here. Okay? This is the amount that the edge ij, the amount associated to the cell ij, would decrease in cost if you included it in your solution set. Okay? What you then do is you want to reduce your total cost the most, so you select the edge with the largest cost with a tilde over top of it. Okay? So what you would do is you then take these exact same U's and V's that we just calculated right here. Let me copy these over. Copy. And you say, hey, I now need to calculate the new stuff. So what I do is when I'm working this, I actually I normally just do all of this work up earlier, and then I have a last column on the side where I calculate all these tildes. So notice we only have 4 cells that are not filled in. So we have the cell 1, 2. We have the cell 1, 3. We have the cell 2, 3. And the last one that currently isn't being used is in position 3, 1. Now, the formula for all of these guys, and let me write that back down, is, in general, we're looking at Vj minus Ui, and then we're going to minus the cost associated with that cell. So this same formula, where's my cursor? I can't find my cursor. That same formula on the second bullet point at the top. Okay. Now, you do not calculate this formula for everybody. You only calculate this formula on the blank cells. These are called your non-solution edges. So non-solution edges, or the not basic variables. So if we go ahead and calculate it in this case, the first one would be V2 minus U1 minus C12. V2 we already found was 15, U1 was 10, and the cost in cell 1, 2 is 6. So when we go ahead and actually calculate that, that one should be, no, it's 2. Excuse me, I read off the wrong cell. It's 2. So this one should be 3. If we calculate the same thing for the next one, and I'm going to go ahead and I'll fill in the formulas afterwards because we're almost at the end of time. This one here would be V3, which is 9, minus U1, which is 10, minus the cost in column 3, which is 0. So this guy would be negative, or negative 1. For C23 with a tilde, this one would be, you're looking at V3, which is 9, minus U2, which is 8, minus the cost, which is 0. So for this one is positive 1. And the last one down there in this blank of row 3, column 1, we would have V1, which is 14, minus U1, which, I went backwards. V1, which is 14, minus U3, which is 9, minus the cost in that cell, which is 5, and we add this all together at 0. Now, here's what this means. The largest change here tells us that we want to use the solution, or we should have included the edge 1, 2 in the solution. So that one says it's your total cost is going to go down by the most. This negative value right here tells you that if you actually included the edge 1, 3, this fake store edge, your cost would go up, because these values are how much your cost would decrease, so a negative means the cost would actually go up. Edge 2, 3 with a positive cost here says we'll probably have to include that edge in the future as well, but it's not the biggest one, so don't use it yet. And a cost change here of 0 tells you use edge 3, 1 or not. It doesn't matter, the cost will be the same as what you currently have. So in terms of the new edge that we want to use, we want to actually use this guy right here. We want to include that cell in our solution. Now, we're going to throw that cell in the solution, but the problem is if we throw that cell in the solution, we actually won't have an underlying spanning tree in our bipartite graph that's behind the scenes, and that means we're going to have an issue. Specifically, it means the solution ain't right, okay? In other words, you're going to have what? You're going to have too much supply or too much demand or something crazy going on. So when we throw in this new edge, we're actually going to have to get rid of one of the other edges, and the edge we get rid of is one of the edges in a circuit that this new edge would have completed, okay? Now, we are out of time for today, so next time what we'll do is we'll figure out which of these cells we're going to toss, because every time you add in a new edge or add in a new cell, you have to get rid of one of your old cells. So what we'll do at the beginning of next time is we'll go through and we'll figure out how do you actually get rid of one of these cells, and then at that point we'll have the new solution, and at the new solution we then check, is this a minimum cost solution? If not, we do this process again. Note, the only thing that you're iterating through with this algorithm is you're iterating through figuring out the U's and V's, calculating the cost with the tilde, and figuring out the new edge to add in and then which edge to delete. All of the other stuff was preliminarily setting up your Tableau, okay? But we'll go through all of that next time. We'll finish off this example. Depending on time, we'll be able to do a second example. If we're not actually talking through how to do everything, it goes much, much quicker. Okay. But that is everything for today. If you do have questions, I'll hang out for a little bit, but there is no more for today.